three things last class.
Explain that.
So like statement for F structure. The rationality statement for.
Yes, I would explain that. Unfortunately, I had absolutely no time to. I barely made it to class this morning. Okay, so but next week is a better. I have not forgotten it, and please, I will myself remember it. But by all means, that's very good. You should remind me if I don't do it. I'll do it myself, and I will write it out. Cannot just explain it in class. Yeah, and there is also that pending exercise that Shant, the one on from chapter 3, right? So I remember it, and I will both of them, and we'll do it. Okay. Okay. Like I said, I barely made it to class, so didn't have any much time for to prepare. So as you probably have noticed, that's not the first time that has happened. But so there are some notes on my home page on differentials and separability. Yes, that's right. I always get confused whether it's a E or an A after the P. Okay. These are it's called some HRI notes, HRI lectures, or lectures at HRI. So these are notes of some 5-6 lectures that I gave at HRI a year ago. They are out of Bourbaki's. They're right out of Bourbaki's. So you could go ahead and read Bourbaki, or you could of course, reading anybody's notes is not like reading Bourbaki, but this could be a place where it might be easier to start reading this than to read Bourbaki. Okay, so this is relevant for what we are going to for these sections. Okay, and in fact, I would say the place to read it from would be Bourbaki, although it is you might have heard that Bourbaki is it's rather difficult to read, etc., but it's also the most beautiful place to read things from, most comprehensive, and once you read it, you're done forever, meaning very likely you won't have to read it from any other book over again anytime. So that's a wonderful thing. I mean that may be an overstatement, but for the there will have to be really some strong reason if you have to read it again from some other book. Okay, so the treatments are comprehensive and wonderfully laid out, and if you can read it, do so. Okay, so it's surprising, right? I mean, on the one hand, so look at the title, differentials and separability. Why did we come up with differentials? We wanted to do calculus, but algebraically. That's why we came up with differentials. Okay, but that is tied up somehow with field theoretic concepts. And rather, there is no connection between tangent space and whether two, field extension properties of field extensions, right? It's at first sight, they are really far apart, right? But there is a connection. So we'll see. Okay, the first few things will be formal. Very important. They may be, I repeat, they are, it's not clear why these definitions, it would not be easy if you ask me so why this definition. The answer would be because it works. Okay, so so let R be a commutative. So we are going to define something called the universal. So something like this. So this is the universal module of differentials. Okay. What you should be thinking, even if you don't know enough, is the following: cotangent bundle. Okay, that's what it is. Okay, it may not be clear. It may not be clear at the end of the course. Okay, but if you just keep this in mind, that this is the same thing as this, and when you see one or the other, and once you see the connection, there will be a moment where you'll say, now I understand. Okay, but so as you very well have experienced by now, often in mathematics, when you make a construction, we try to look for the universal object, some kind of a universal object that does everything for you, right? For example, what is tensor product? Tensor product is a universal object which, in fact, let's put it this way. It's a universal object which does something that you don't know in terms of something that you know. What the tensor product does for you is converts bilinear maps to linear maps, right? Similarly, I don't know if you have seen this, but for example, if you read a little more in this direction in the book, there's something called the universal enveloping of algebra of a Lie algebra. It converts maps between Lie algebras into it converts say, let's put it this way, it converts the representation theory of a Lie algebra into the representation theory of an associative algebra. Okay, so and so tensor product is something that you've seen. I'm sure you've seen other things. For example, localization, that has a certain universal property, and although it might not be obvious, you might if you look at it, you can phrase it that way. Okay, so this is going to be a universal object. What it does for you is it will turn differentials, derivations into linear maps. Okay, so so just like tensor product turns bilinear maps, or more generally multilinear maps, into linear maps, this turns derivations into linear maps. So it turns derivations, of course I'm being a little loose here, but into linear maps or module maps. The word linear is also applied even in the case of a module. So not just in the case of a vector space. Okay, so we have so what's the so this is our R is a commutative ring with identity. Most often in our not always, but even in the case when it is a field, what we are going to say makes sense, and for a first pass maybe you should just look at it, say assume R is a field. Okay, so A is a commutative R algebra. So what should you be thinking of? For example, A is the ring of functions on an affine variety, okay, or equivalently a reduced affine algebra. He is not assuming reduced because it's not necessary. Okay, so e.g. kx for an affine variety x. It okay, yeah? Okay, so we want the following property. So we have the notion of a derivation, right? So this is an R derivation. So M is an A module. So in this case, R is commutative, so left or right doesn't matter, but let's say left, we write it on the left. R derivation. What does this mean? Let us recall what this means. It's an R linear map, right? What does this mean? It's an R linear map. So A and M are in particular R modules because R is so commutative R algebra means there is an algebra ring homomorphism from R to A, taking unital ring homomorphism, which makes A into an R module, and you can also turn M into an R module by just restricting the structure to R. Okay. So R linear map, and then there is the Leibniz rule, right? D of AB is dA BdA plus AdB. Okay. Now what we want is something with the following property. So I want a module and a D does he use DAR? Yes. Right? Which is universal. That is, give me any derivation to any module. I must have an A module map between this and this, such that this unique A module map between this and this, such that the diagram commutes. Okay? So want the following, that there exist unique A module map. So I want some A module and a universal derivation, meaning an R linear map from A to that module, that A module, satisfying the Leibniz rule, with the property that give me any other derivation to any other module, there must be a unique map from this to that, unique A module map from this to that, which such that the diagram commutes. A module map such that, so you have DAR here, such that this diagram commutes. So the dot means there exists. Okay, so let's think about this for a minute. Let's even take an example. and try it. Okay? What's the simplest example? Let us take A to be R to be K. K is a field. Okay, algebraically closed if you wish. That doesn't matter for our purposes here. Let us take, what is the simplest kind of A that you can think of? Suppose I can take A to be K itself. Then it's rather trivial, right? What would the universal derivations be then? Okay, suppose I take R to be K and A to be K itself. Okay, then if you have a K derivation, what does that K derivation do to scalars? It's a derivation, it's a derivative. Derivative of a scalar constant is 0. So it kills that. So the omega K over K is actually 0. Right? You can take, if I take this to be 0 in that case, and this map to be 0, it will have that property, because whenever you give me a derivation, that means K that's the 0 map, and it factors through. So that's not interesting. So interesting, although it's not entirely uninteresting. You have to observe that the derivations kill R 0 on the scalars. Scalars here meaning R or K. Okay, let's take, what's the next example? What's the next simple affine variety that you know? What's the simplest affine variety that you know? I mean, a few points maybe, but let's take something more one-dimensional, simplest. Affine line, right? What is A in that case? Kx. So why don't you try for 2 minutes how you would go about doing this? So I want Kx here. Let us think like this, right? How much choice do you have? Suppose I give you a derivation from Kx to M, right? It's a derivation. So what do you know? It's like a D, right? It's like a D. So, you know, so here you should use all your calculus things that finally, you know, in school probably you wondered what, some people, we wrote say du by dx, and then the teacher told, we are told that du and dx, it's not like you're dividing du by dx, it means it's a limit, etc. And then conveniently at some later point, du and dx are separated, and you have integration with dx hanging out at the end without any du, etc. Right? And we've often, I guess, it happened to me, and I'm sure it's happened to you too, what this is all about. Right? It somehow seems to work, but it doesn't, it's never satisfactorily explained. Right? So here finally is some satisfactory explanation of all the notation. Right? It's remarkable that of course these are all 20th century inventions, these devices, but this notation apparently is due to Leibniz, who was a contemporary of Newton. So it's amazing how sort of without formally thinking through all this, you had devised a notation which sort of suggests it, and finally that notation took centuries for it to be for it to finally get a hold. This is what is happening. This is how to think about it. That for that to happen, it took centuries. Right? Okay. So this is the time to sort of leave out, without inhibition, use all your tools that you learnt in school or in advanced calculus, right? So d is a derivation. So how does it act on, say, d of 3x square plus 5x? Something like that. What would I do? I would write 6x dx plus 5 dx. Right? If you want one more step, if you put this equal to u, you would write du by dx is equal to 6x plus 5, and then you would write du is equal to 6x plus 5 dx. Right? This is what you would write. Okay. What is this telling you? So now the point I want to make is, this follows once you have said that d follows the Leibniz rule, this follows. You have no choice. Okay? So that I'm not doing, but that this must map to this. So now dx is an element of M. So this makes sense, because this is this element of M multiplied by 6x, which 6x is an element of kx, right? This is an element of kx, and so this makes sense, right? Is this clear? So how much choice do you have? Where can you send a polynomial? It is sent already. The only choice you have is where that dx. Okay? This is somehow, so it is really, the answer is, and dx you can send anywhere. So dx can be any element of the module. So in other words, therefore, if it's a module map and you have 1 degree of freedom, so to speak, then it must be a free module with one generator, right? So this one must be a free module. So this kx over k is a free module, free kx module of rank 1. And it is the natural thing to write for that is, for the generator, is the notation dx. That's a notation for the generator. Right? Of course you can write whatever you want, but it is most natural to write dx. So with that notation, all the, that you've intuitively all the reactions that you do, that all the calculus that is now part of your second nature to you is all validated and it's all correct and you can use all of them, right? Okay, so somehow this must be, right, what is this? This is kx free module, so I'll write dx, right? And let us verify that indeed that has the property, right? Where do I send dx? I send dx to where the d sends x, right? D sends x, and that's it. So there is a unique map, right? And so this, what is this map? This map, this should be a derivation. I send f to f prime dx. AR depends on R and A. It does not depend on M.
So what does that dx there mean?
Which dx there mean? This dx, okay. This dx is just notation. So you can.
So what is this?
Yes, that map is f going to. So f is a polynomial. And it goes to f prime, which is your formal derivative that you can take. Now derivative is just, although here it is formal. Derivative of a polynomial, you just formally take derivative, okay, which you can, x to the n is nx to the n minus 1, and then dx. You add a dx because it has to be something times dx. Now that thing is a formal symbol, right? Okay. Now this has the correct property, right? Because give me a D, there is a unique map here. This is the rank 1 free module. I have to send dx to there. And does f go to f prime dx? F indeed goes to f prime, the image of x under D, this D. Okay, so this dx I'm using in very many different senses. dx is the image of, is also an element of M. It's also an element here. But you get the idea, right? It's a very nice abuse of notation, right? And here is the way to think about this. What is this? At every point, somehow, see, you have one tangent direction, right? It's an affine line. At every point, there is a tangent direction, right? So there is a concept called tangent bundle, which puts all the, so tangent space was a linear space of dimension equal to the dimension of the manifold, right? So I'm using these terms in a loose way, so you should just take that intuitively. So if it is an affine line, at every point the tangent space will be one dimensional, right? So you should, although the tangent vectors seem to be going this way, because to distinguish the tangent vector at this point from the tangent space at this point from the tangent space here, you think of them sort of vertically sticking out. You could, right? So you have the tangent bundle, therefore will be this line along with a one-dimensional thing sticking out. This is a very vague picture, it has more structure to it. Now there is something called cotangent space. So what was tangent space? M mod m square dual. Cotangent space is easier, it's m mod m square. So there is also a cotangent space which at every point is the dual of the tangent space. So at every point, that's also one dimensional, right? And so it is, so this object here somehow is the algebraic version of that cotangent bundle. So the fact that it is free of one dimension says that it is Well, its free says that it is actually what is called a trivial bundle, but never mind, we are getting far ahead of ourselves. Never mind that. But I hope I have given you some idea of what to look for, right? So you have you can imagine a cotangent bundle of a manifold. That is, at every point you have the dual of the tangent space sticking out, and you put them together in some way. Okay, if you do this algebraically, the way to do it, or rather the way to do this algebraically, is this object, this omega AR. That's why I said in the beginning that it is, you should think of the cotangent bundle. Okay? Okay. Now, next complication. Let's do one more level of complication. Okay? How about I take a curve with some equation. So, of course, we could take next an affine 2 space, try it with kxy. What do you think will happen? So I have to do d of f of xy. Right? What will this be? What do we know? Is del f by del x dx plus del f by del y dy. This follows from the Leibniz rule. So we will, the only choice again, once I know where dx and dy go, I have literally the rest is fixed, right? So what will omega k xy over k be? This should be, this is an A module, right? This is an A module. So it's kxy. It's a free module with 2 generators, and the generators I will denote very suggestively by dx and dy. Okay, so it's dx plus direct sum. Of course, I also have to, that is not by itself good enough. I have to also tell you this data, the map, right? So what is this map? D of kxy to k of an fxy equal to, what is it? That's given by this formula. Right? Okay. Let's do one more level of complication. So affine, it's clear now how, and here again, it's natural that everything is falling into place. We have intuitively, we have a 2-dimensional, intuitively, at least intuitively, we have a 2-dimensional tangent space at every point of the affine 2 space. So the cotangent space will also be, it's a dual of that, it's also 2-dimensional. And it is spanned, these 2 free generators dx and dy are the generators of that cotangent space. Okay. Again, that's not being very precise, but that's just motivation. But I hope it is now clear what omega kxy in any number of variables over k will be. It will just be a free module in as many generators as there are variables. Okay. Okay. What other affine? Now let's look at an affine variety. Affine spaces are, of course, the first thing to try, but now you see that they are boring, right? We know how it works. Okay, so let's go to the next level of complication. Yes?
Can we already see that it's a kx linear map?
Which one?
So in this case, say.
Oh, this is not a kx linear map. This is only a k linear map. This is a derivation.
But
Oh, this one. Okay, this is a kx linear map because it's a free module.
Here is a here what it's a kxy.
Yes, it's a kxy linear map, and it's a free module with so many generators. So I am to specify a linear map from this to M. It's exactly equivalent to specifying the images of dx and dy, and I send them to wherever they have gone on the derivation. It all fits in very smoothly and cleanly. Okay, clear? This of course is not a linear map. This is a derivation. Okay, this is only a k-linear map. All right? Okay, good. So how about we try an actual variety, not just an affine space. So again, I keep forgetting. How do I write this? Y square is equal to x square plus something like this. Right? This is something like that, or y square. The other famous one called the cusp, which looks like that. So what do I mean by that? This is my x, right? So A I take to be kx. So it's a k algebra. I want the module of differentials on that. So let's think. Okay, I'll not write this. So one of these. Let me call this phi or something. Phi is either this or this, right? I'll just call this phi. Of course, you have to check that that is a it is reduced and all that, right? What I'm going modulo, but never mind. We just assume that it is. Okay. So this is what we have. I have a module m over this. So this should somehow okay. Now what we are looking for is some object here, right? Which is so this is what we want, right? Okay. So and I such that this holds. Okay. Okay. Now I put this because given a module, so this is a derivation from this to this. Right? This is a module over this. This is a derivation from this to this. This is a ring map. So you can also think of it as a derivation from here to here. Correct? So this one will be a derivation. Okay? This being a derivation, from its universal module of derivations, there will be a map. Right? So you have this. So I'm not writing this very right? And it is natural to expect this. So what should happen? So I'll say it. So after a while, after you think about this for a minute, you will come to the conclusion, or at least it's natural to guess the following, namely that this object should be a quotient of this object, right? Should be a quotient such that so what you go modulo is killed by, it becomes a module over see, if I take a module m modulo im, m modulo im is a module for r mod I, right? So it should be a quotient of this, which becomes a module over this, and with the property that whenever the derivations are factoring like this, through this, I'm not saying this very well. So then somehow they, the quotient, so what should you quotient by is the question. You should quotient by something appropriate, so that precisely though, the what is 0 is precisely what is 0 when, okay, I'm not saying this very well, but it's clear that should be somehow a quotient of the big one. Let's see what quotient it should be.
So we know that phi should go to 0.
Phi should go to 0, exactly.
So firstly, maybe Rakasan is asking me just like a module generated by the image of phi under that path. K.
Yes, that's a natural thing to expect, but indeed the point is that phi should go to, here phi is going to 0, right? So natural to expect that phi should go to, so indeed that's the answer. So here is let's try it out. Okay, so what I want to claim is k xy. Okay, let's give this, since there are too many going, so let's give this a name. A is equal to kxy by phi, right? I put A equals kxy by phi. So I want to realize this as so I want to write this quotient. Okay, now so think of phi here as phi is of course 0 here, right? When I write phi, I mean the image of phi in A, right? Phi is a polynomial. I mean, if I write that polynomial, think of it as in A, it's 0. So d of that is 0, right? So here, if I write d of phi, right, that should go to 0 here. In other words, what you see is that you can write a d of phi here. It's an element here, right? For example, let's work it out. If it is y square minus x3, phi is y square minus x3. What is d of phi? D of phi is 2y dy minus 3x square dx. Now, how is it an element here? Well, this is a free module with two generators, dx and dy. So minus 3x square is the coefficient in front of dx, 2y is the coefficient in front of dy. That is this element. Okay, that better go to 0 here, because d of phi is always 0. Okay, so the sort of guess, first guess at least, is that this should be so let me write it like this. So is this clear what this means? This is the submodule generated by d phi. Okay, but okay, there is a slight problem with this. The problem here is that this is not what I want. What do I want this to be? I want this to be an A module, right? It's not quite an A module yet. What is it right now? What is it a module over? It's a module over kxy at the moment. How do I make it into an A module? Okay, so okay, maybe each of these steps, actually if you think geometrically, each of these steps has meaning. Okay, maybe I'll attempt it, although like I said, I'm not being well prepared, I might stumble, but nevertheless let me try to attempt it. Okay, so suppose this is my curve and you should think of this as sitting inside A2. Right, this is my picture for A2, this is my picture for my curve C. Okay, now we saw that the tangent maps, at the level of tangent maps, they go this way, right? If you have a map between manifolds and you have a point here and a point there, then the tangent space, then there is a natural map from the tangent space at this point to the tangent space at that image point there, correct? That is the differential map. Okay. But on the cotangent level, there is a reverse map. Okay, so in other words, so this is an inclusion. Okay, so let me okay, so maybe I'm not it's not quite as I expected it to be. It's slightly different, but here is one way of thinking about it. So when you have a map between geometric objects, if I have some kind of a bundle on this, you can pull it back. This is a very simple construction. This is just it's like pulling back functions, right? You have a function here, I compose and I get back a function on this, right? So similarly, what is a bundle here? It is at every point, at least intuitively, it is just at every point a tangent space. So what do you assign to a point here? Well, you look at the image, look at the tangent, whatever is associated that vector space at that point, assign it here. It's as simple as that. This is just the dumbest way to do things. Okay, so you can have a cotangent bundle. So a cotangent bundle here could be pulled back to this one. Okay, that would be like saying without this is the cotangent bundle here. if I tensor that with A, that becomes a free module over A in two generators, right? If I have a free module over some ring, if I tensor it to any other ring, right, this might be, that ring might be a quotient, as in this case, never mind. But that what you will get is a free module with two generators over that ring. What is the corresponding geometric statement? It means that I'm pulling back the cotangent bundle here to the cotangent to this thing. So at every point I have two I have a thing which has two free so I've pulled back the cotangent bundle, so at every point there is a two-dimensional space sitting there, okay? But what I want is, see, the tangent space, or maybe it's most natural to think of pulling back also the tangent bundle. So think of for a minute of pulling back the tangent bundle. The tangent bundle, you similarly would also get two-dimensional things, right, at every point. But the tangent bundle of this particular thing is only this tangent line, right? In that, so, right, it should be a sub of that. It should be, when I take the tangent bundle of the sub, that should be contained, meaning in the sense that at every point it should be, whatever I associate must be a subspace of the pullback, right? That's what it should be. And the angle at which this line is inclined should depend on the slope of the line. In other words, something to do with the equation, right? Okay. Now this is the tangent picture. In the cotangent picture, what should it be? Because it's the dual, it should be a quotient of that, right? It should be an appropriate quotient of that. And what quotient? It is this quotient. So if this is an element here, so if I go modulo this and tensor that with A, that indeed is a module. No more, once I have gone here, it is no more free, right? Before I do this, it's free. But after I do this, it's not free, and it's in fact taking care exactly, if you work it out, of the correct constraint, right? Okay. Oh, I'm afraid that was not great, but hopefully that's useful. Okay. Now, in the book, all this is done as lemma. If you read 4.2.4 in the book, it goes through this, but without these little bit, he just does the general case all at once, okay? But I somehow feel that thinking in terms of examples, these basic examples, is much more, I would, when you read the proof, do think of, I mean, of course you can do the general case, but think of some special, very special cases, and you'll see that for most people at least, it's true that you will learn more by just trying that example yourself, or following the proof in the case of that example before understanding the general example, the general theorem. Okay. Now, okay, as an example of how different mathematics is, this is how you would think about it, right? You would do kx, you would do kxy, or you would take a simple curve and try out what it means, right? If you were confronted with the problem, right? Now, the book, however, starts with the general solution, which is completely, doesn't make any sense whatsoever, but it works, okay? So it's the general solution to the problem, okay? So for any A, any commutative algebra A, R is any commutative, etc. But what is really, more intuitive and more illustrative, at least at the beginning, is this 4.2.4 lemma. What is the module of differentials of when the ring of functions on an affine variety? That's the question. And the answer is, you take the as many free generators as the an in which you are sitting, in which that is embedded, and then go modulo d of f1, d of f2, d of f3, d of f4, as many equations are you. Here we had just one equation, but if you write 10 equations, you would go, each one would pose a constraint. You would have df1, df2, df3, etc. Okay, as you will see, this will lead us to the notion of smoothness. You can define smoothness and what is called Jacobian criterion for smoothness, etc., which are very basic things in algebraic geometry, but it will naturally lead us there, this idea. Okay, so let us do now the formal construction of this universal module of derivations omega AR. Okay. Of the universal module So one comment here is, so it is defined by a universal property, right? The omega AR is defined by a universal property. That is, it is that object. Of course, it's not just a module by itself, it is the module along with the derivation. Yeah. So it's A along with the derivation, R derivation, the universal one, with the property that if I have any other module, A module M, and a derivation from A to M, there is a unique map. Now, you might have seen that such a thing is always unique if it exists. Unique up to unique isomorphism. Right? Because if there was another module, there is a D prime and an omega prime, then by the universality of this, there would be a map this way, which would make it commute. By the versality of this, there would be a map this way, which would make it commute, right? But this, if I take the composition here, that would be a map from this to this with the property that if I put that map here, these things would commute. So if I put D here, and this composition here, this triangle would commute. But if I put identity here, it works. And we have said that there is a unique map. Therefore, that composition must be the identity of omega. And similarly for omega prime. And therefore, it's clear in any such, this is a general proof for any such situation that such an object, if it exists, is unique up to unique isomorphism. Okay? So that is general nonsense. So all we just have to do, therefore, is construct it. Right? So how do you construct it? It's a highly non-intuitive construction. Well, once you understand it, it's you can make sense of it, and in fact, it comes. You can think geometrically about this, but let's write it down. I mean, definitely not as how to say, as appealing maybe as the other one at first sight. Okay, so you have the multiplication map. Right? What is the geometric when you have a multiplication map? What is it geometrically? So, for example, if A is the ring of functions on an affine variety, this would be kx tensor kx to kx. So, kx tensor kx is the ring of functions on x cross x. So, what is the map from x to x cross x? It's the diagonal. So, there is something to do with the diagonal here. Okay? Remember that you might have studied that something is Hausdorff if and only if the diagonal is closed, right? So the diagonal has lots of things, thinking in terms of the diagonal has lots to do with geometry. Okay, so this is it's hidden there. So it's somehow something to do with the diagonal. Okay, so now let I be equal to the kernel of this map. What is I? I mean, it's an ideal. Ideal in where? Ideal in the algebra A tensor A. Right? So this is a map of algebras. So it's a ideal in the algebra A tensor A. Somehow, so what are we trying to get? I'm trying to get a module on A. Right? Again, geometrically, what is I? It's the yes, it's the ideal of the diagonal. Okay? So x cross x, inside that x is sitting as the diagonal, and so it's a subvariety, and this is the ideal of that subvariety. What do I want? I want I want a module on A, not on A tensor A, right? So finally, the module of derivations should be is an A module, right? Right now, I look at it as a ideal. Therefore, it's a module for A tensor A. To turn it into a sort of module over A, what do? I go I modulo I square. Suppose I take. So I take I modulo I square. Now, this is killed by I. So this is still an A tensor A module. So it's killed by I. But the fact that it's killed by A means that structure passes to A. So this becomes an A module. Right? So indeed I have an A module. So the claim is, so you set this equal to omega. Okay, so let's spend a few words there. Okay. So I is an A tensor A module. And I mod I square is an A tensor A by I module, and so an A module. Okay, so somehow this I tensor I mod I square. So this idea that this has something to do with cotangent bundle. This is the idea, you know. I'm afraid I'm not able to make this more justify why this is so. But the fact that this definition is saying that at least after you stumble upon it, you see that this has something to do with the cotangent bundle. Okay. Okay. Now, so is this? So it is an A module, right? I have constructed an A module. Now I have to construct. I have to construct this, right? So what is that? So D from A to I mod I square is A going to A tensor 1 minus 1 tensor A bar. Now let's observe that, yes, I mean, I understand, I would be mystified too. This is all magic of algebra. It just works, right? Everything falls into place. Okay, that's all one can say. So this is A tensor 1 minus 1 tensor A. Notice that this is an element of I, because A tensor 1 goes to A under multiplication, 1 tensor A goes to A under multiplication. So the difference is in the kernel of the multiplication map. So it's an element of I. So I can think, then I can take bar on it. It's just the element, corresponding element here. Okay. So right. So there you go. That's the construction claim. So we have to still prove that it is it's a derivation and it has the right properties. Okay. So that is sort of easy, but let's do it. Okay. Why is that? Okay. All tensors here are over. What should I say? All the tensors are over R, right? All the tensors are over R, right? So it's not written there, but all tensors are over R. So this is tensor over R. Okay, you can assume R to be K without just for, if that increases your comfort level, go ahead and do that. No, nothing wrong with that. Okay, let's see. Why is this an R linear map?
So pull out the linear factor for both. You want to see what happens to RA?
So I want to say, sorry, 1 second. So I have to see no, I'm not following what you're saying. Say that again.
So you want to see what happens to, take some little argument to R. You just want to see what happens to RA under this derivative, under this D.
Okay, good. So, right. So you just formally checking it, that it works. Right. Okay, very good. Let's do that. So D of R A, let's compute it. Right. Okay. Yeah, after you become a little older, you never think of doing the obvious thing. right, and that's, of course, you can pull out the r from here and pull out the r from here. And that's so that's R of dA. So what we are saying is, even at the level before, so there is a map from A to A tensor A itself, which is this map, which is R linear. Just one second. Why am I? Why I can make the one is a well-definedness is a problem, right? Or is it not? Well, you can just check. Well-definedness of this map, A going to A tensor 1 minus 1 tensor A. Is that a problem or not? No, I guess not. So you just add and you just check that it is additive morphism. It is a so I have to define a map from A tensor A to A tensor A, which I write like this, and I check that it is an R module R linear map directly. But this is the checking that it's R. I of course have to check that it is also additive, right? So d of A plus B, I have to say, is d of A plus d of B. Okay, that's also quite obvious. Okay, so it is a right. So, and why is that a derivation? So D is, so far we have checked that D is R linear. So D is a derivation. So let's check that. So what do I have to check? D of AB, right, is AB tensor 1 minus 1 tensor AB. I'll forget the bar. And on the other hand, I have to check B dA and A dB. Right? What is this? BA tensor 1 minus B tensor A. And what is this? AB tensor 1 minus A tensor B. Okay. Now if I add these two, I want to get this one. Maybe I've not done this correctly. Is this A in the second spot? This looks okay, right? And maybe I have to look at it bar.
You can't use the B inside the again. B times A tensor 1 minus 1 tensor. I mean the tensor is over R, so DA is A tensor 1 minus 1 tensor A. BDA is b times a tensor 1 minus 1 tensor.
Okay, let's see. It's b of a tensor 1 minus 1 tensor a. Okay, so I see what you're saying, but I'm allowed to be a little cavalier because I am taking the bar. Okay, so you're right. The point well taken. Okay, so let's do this, but okay, let's write that. Okay, but the point is I'm going modulo I, right? So this is on the bar. So what I have is actually I have bars here. So let us check something about bars. So at that level you can be a little looser. So let us see what okay, what does A times B tensor 1 mean? Well, this right. So this could mean A tensor 1 or 1 tensor A, right? So you see, this is not clear at all, because how is this an A module? Right? So at the without the bar, if I am thinking, what is A? What do I mean by B of A tensor 1? What do I mean by that? B tensor B times A tensor 1, I'm afraid not. It could mean, okay, so so the question is, how at all is A tensor A an A module? Okay, to make A tensor an A module, you must have an A algebra map from A to A tensor A. Now there are two ways to do it. One is A going to A tensor 1, the other is A going to 1 tensor A. No, that won't be an algebra map, I'm afraid. Or will it? Maybe that also is an algebra map. Okay, it will fail to be. Okay, the problem is it will fail to be R linear. Because there you go. Correct. Yes. So, yeah, I was thinking R linearity, but Z linearity is what you're thinking of. Correct. Absolutely. Yeah. So that it seems like multiplication is okay, but it would be a problem. Okay. So so there are two. So this could be. So this is B tensor 1 times A tensor 1, and then it's equal to BA tensor 1, right? Or it could be 1 tensor B times A tensor 1, in which case it will be A tensor B, right? Now both these are okay, because bar, when I put the bar, I claim both are okay. Now why is that? Because I am going modulo Right. So what's the B tensor? Say that again. B tensor?
B tensor 1 is same as 1 tensor B, meaning B tensor 1 minus 1 tensor B belongs to I.
Belongs to I. Exactly. So exactly. B tensor 1 minus 1 tensor B belongs to I. Therefore, this B tensor 1 minus 1 tensor B into A tensor 1 belongs to I. So modulo I have B tensor 1, so that is BA tensor 1 is equal to A tensor B modulo right. So with that in mind, let's do this calculation. Let's see. I hope I will get this right. So I want to see that these two are equal.
I think you can see that those two are equal, but some others.
Okay, go ahead. Yeah.
This thing you can see that they're equal because I mean A is commutative, so BA will be same as AB.
Absolutely.
So A tensor B, B tensor A, they're both.
Absolutely. You can see that otherwise too. Yes.
So,
Yeah.
so just adding these two, then
So so let's see. So this is the same as this. If I want to, or maybe better to make this. This is the same as this.
B times 1 tensor A is same as A times B tensor.
Okay. So this is in I mod I square. I have to think of.
Those two terms. Oh, that's right.
Okay, so the claim is somehow, okay, this shows I should have prepared. So somehow this shows that this, though the equality holds in I mod I square. That's where I need to check. Okay, so rather than struggle with this, I'll let you do this. I will also try to do this myself and write it up. Okay, so and it has this universal property further that if I have a derivation from so let's see at least if that is clear. So if I have from A to okay. Okay, so the most natural thing to do is perhaps just to define it on, given a derivation D, define it on A tensor A itself. Restrict it to I and see that it factors through mod I square and therefore becomes an A map. So I repeat, so D of A tensor B you will write as A dB plus B dA. You just define it like that and then you check, you restrict it to I, and then check that it is mod I square. Okay. Again, I'm sorry, I should be better prepared to do this. So I will either write it up, or failing which, we'll just quickly do this next time. Okay. So the point is that there is this construction which will does the universal derivations. Now also I may not further discuss 4.2.4, which tells you what omega A r is when A is a affine ring of an affine variety. Okay, because we have done those examples, and there is the, so it's clear how the general thing will work. Okay, so that part I will expect you to read. I will not spend too much time on that. Next we will take up the case of fields, and also the Jacobian criteria, definition of smoothness of a when a point is smooth, when a point on a variety is smooth, etc. Okay. Okay. So see you then. Yes. I mod I square to m. Okay. So I'm not terribly clear, so don't hold me to this. But right now, the most natural thing would be to see. So A tensor A to m, I try to define a map. Okay. So that's, I'll send A tensor B to dA B, or A dB plus B dA. Right. What kind of a map is it? It's only an R linear map. Okay. Because D, so at that level it's okay, that will follow from the tensor product, because D is an R linear map. So if I send A tensor A to A tensor B to A dB, say, that will be a bilinear map from A cross A to M. Therefore it will be a R linear map from A tensor A to M. So if I write A dB plus B dA, that will be an R linear map from A tensor A to M. Okay, just from the property of tensor product. Okay, now I can restrict it to I, and then check that it's actually 0 on I square. Okay, so it will factor through I mod I square, and therefore it will be an A modular map. Okay. And yeah, so also it will lift this because A has gone to A tensor 1 minus 1 tensor A, right? And where do I send this? I send this to okay, so okay, I seem to have made another mistake. So A tensor A to M, I should just take, okay, so A tensor B going to A dB, just take that, okay. So where does this go now? This goes to A D1 minus 1, okay, or maybe the other way, B dA. So B dA, so it's 1 dA minus A D1, but D1 is 0, so this goes to dA. Okay, so there is some, you have to, right, it's just a, you have to just get the algebra to work right. Okay, but it's, but anyway, we'll quickly, either I will write it up or I will quickly go over this next time. So what's coming up is, I repeat, so separability and such notions of field theory from the point of view of differentials. I repeat, this is interesting even if you're just plainly interested in field theory. If you want to study those such questions in field theory, these ideas are, one can say, even indispensable. And moreover, it leads naturally to the notion of when a point on a variety is smooth. Okay, we will learn the Jacobian criteria for smoothness. Okay. So that's what is coming up next.